Welcome to this lesson on radioimmunoassays. It's a protein quantification technique, and radioimmunoassay is based on the basic immunoassays, which are biochemical tests that we use to determine the concentration of substances in a fluid like serum and urine using the antibody-antigen reaction principle. The immunoassays are able to quantitate as well as to detect the analyte, and they have been the method of choice to especially determine very low concentrations of specific analytes. Such analytes would include like drug assays, hormones, specific proteins, tumor markers, and markers of cardiac injury. So now radioimmunoassay is remarkably sensitive, and it uses an active and a radioactive material. That's why the name radio, and then immuno because of the antigen antibody binding theory, and then assay because of the detection of compounds. This technique was first introduced in the 1960s by Bierson and Yalo, where they were trying to concentrate or to determine the concentration of insulin in plasma. So Dr. Yalo was the first female to win a Nobel Prize on her work with radioimmunoassays. So radioimmunoassays, generally abbreviated as RIA, combines the specificity of antigen-antibody interaction, because specificity allows us to differentiate our analyte of choice from others, and combines this with sensitivity of the radioactivity measurements, so that it's able to measure very little amounts. It is a technique used to detect micro quantities. It's highly sensitive for proteins, viral antigens, antibody, structural proteins, vitamins, drugs, and metabolites. And it can be used to detect even picogram quantities, that is 10 to the power minus 12 of a gram. You can see that makes it highly sensitive. So the principle of this assay is based on competitive binding. This is binding principle. It's based on competitive binding principle. And in this competitive binding principle is where there is competition of unlabeled analyte, or what we call unlabeled antigen, with a radiolabeled antigen for limited antibody, and therefore the increasing unlabeled antigen concentration usually will inhibit the binding of the radiolabeled antigen to the antibody. Let me illustrate by first looking at what are the requirements of this particular assay. We need radio-labeled antigens. Here they are. Now we can label them with tritium. We can also label them with iodine 125. Then we need specific antibodies, which are now specific for the antigen that we have chosen. Then we have, so these are our antibodies. Then we have our unlabeled antigens. So we have one that is bought or manufactured, and there is now one that is coming from our sample. This is our sample. This is our, what you can call a standard. And standards usually have known concentrations. We need a microtiter plate, and we need washing buffers, such as the 1% trifluoroacetic acid. So step number 1, this is your microtiter well. So you label it with you bind your antibody there, and then now you add your radio-labeled antigen. And of course, they're going to bind on the specific sites of your antibodies. So once you measure radioactivity in this case, then you're going to get 100% radioactivity, because your radio-labeled antigens will occupy all the present antibody sites. Then number 2, you now add to that well, you now add your unlabeled antigen. This is the one that you have commercially obtained. So it's not from your sample. So this is a standard. This is a standard or known. And you can see in this case we have the known is 1 nanogram. Yeah. So you add it to your well. And because it's based on competition, it's going to replace the concentration of 1 nanogram is not very high. So the competition isn't so much. It's going to replace some radiolabeled antigens, and then now you measure radioactivity. So in this case, we are going to have radioactivity that is less than 100% because we have some areas of our antibodies that have been occupied by the unlabeled antigen. Yeah. Now you repeat that process with different concentrations of your unlabeled standard. This is our standard. Okay. So we started with 0 standard where we had 100% radioactivity, went to 1 nanogram, which is about 90%, 2, 3, 4, until 7 nanograms. And you can see that now when you have 7 nanograms, we have a radioactivity of about 30%. So what you do now with this is you generate what we call a standard curve or graph. So in this case, you get a linear graph like shown here. Okay, so you have your linear curve. That is the percentage radioactivity on the y-axis, and the x-axis has the standard of the unlabeled antigen. Now, next is now you go back to your sample. This is your serum sample that should be having the same antigen as the unlabeled antigen that we have used as a standard. The only difference is that in this case, we do not know the concentration of this antigen. So you start again like we did before, where we have your microtiter plate coated with your antibodies and having the labeled, radio-labeled antigens bound to the antibodies. So you add your sample, and now you're expecting, depending on the concentration of your A antigen in this case, then you're going to have the different replacements of the radio-labeled. Okay? Now you have added, and then you measure radioactivity, and in this case, we are able to get about 40% radioactivity. So what you do, you go to your standard curve that you have already generated and go and locate the 40% radioactivity. So this time what we don't know is the concentration. So from the 40%, we will extrapolate our graph to the standard graph and then extrapolate it to the x-axis to get the concentration. So now the concentration of our serum sample has 6 nanograms of the antigen. Okay, so the advantages of this test is that it is highly specific because we are looking at using antibodies that are specific for the antigens. Highly sensitive because using antibodies of high affinity, it is possible to detect even a few picograms of the antigen in the tube. It's highly accurate and precise. The disadvantage is that using radioactive materials is a radiation hazard, and then it also requires trained personnel, and labs require special license to handle these radioactive materials, require special arrangements for requisition, storage, even disposal because of the hazards related to radio labels. Okay, that is it on the radioimmunoassay and how we use them to estimate the concentration of our analyte, which can be an antigen, can be a protein, can be drugs, can be a variety of substances. Thank you very much. Let's meet in our next lesson.